Thank you very much. It's such a pleasure to be here. It's my first visit to Princeton, and I walked around yesterday, and it's just gorgeous. So happy to be here. Yeah, so what I want to talk about is how the chemistry that happens at the early stages of planet formation, how that affects the kind of planets you end up with. And I will be mostly talking about theory and observations today rather than laboratory studies. And the reason for that is Alma. That as of a few years ago, we have this amazing new set of eyes on the chemistry of star and planet formation, which is Alma down in the Atacama Desert. And it's just, I mean, in astronomy, whenever you get an order of magnitude improvement in sensitivity and resolution at the same time, you're going to see new things. And we are seeing new things. So that's going to be most of the things I talk about. But I am going to try to emphasize also where we need laboratory work and give you some ideas of what we are planning to do there. My own laboratory has been up and running for about a year. We're still sort of the version, I think 0.7 maybe, compared to the what was planned when I applied for the Harvard position. But we are making strides forward, and I think combining these laboratory results with these new fantastic telescopes in the next few years is going to be really powerful combination. Before getting into the talk, I just want to take a moment and acknowledge that, as is common for observational and laboratory work, this is a team work, and I have a fantastic team at Harvard that is responsible for most of the results that I will be showing today. And of course, having funding is very important. So I'm also very grateful to the Simons Packard and Sloan Foundations for helping me there. So the fundamental, there are two questions that bothers me and that I try to address in different ways with this research. One is that if we look, even if you just look in our solar system, we see very different planets. And if we expand our view to outside of our solar system, we see even more kinds of variety in what kind of planets and the planet compositions that we find. So, and this is something we would like to understand, right? Why we end up with such different planets. Why planet formation, which we think start in the same way fundamentally, why it can have such different outcomes. So that's question number one. That why you get such different basic bulk compositions of planets. The second question is zooming in on a very small but very interesting subset of planets, that is rocky planets in the so-called habitable zone, and what kind of compositions they will have. So the habitable zone is defined as the temperature range around a young star, or like around any kind of star, where water can be in its liquid form. And we think that is a reasonable criterion for habitability, not just because life as we know it here on Earth relies on liquid water, but water is just such a fantastic solvent. So if you want to have a rich and diverse chemistry, you want to have liquid water as your solvent in which that chemistry takes place. But this kind of habitability criterion doesn't really matter if you don't have water in the first place. I mean, it doesn't matter if you have liquid water, if you can have liquid water if there is no water around. And second, this habitability criterion doesn't really matter if you don't have the building blocks of life, that is organic material, since the whole reason we wanted to have liquid water is for organics to be able to meet one another in an effective way. So the second thing that I want to talk about is thinking about habitability, sort of chemical habitability of planets that are in this sort of physically habitable zone. And the underlying theme of this talk is that, which I think is a common sense one, is that the composition of planets are fundamentally set by the compositional material from which they form from, which means the composition of protoplanetary disks. And this is obviously a cartoon, but what's really exciting is that with Alma, we can actually start seeing this, and I'll come back to that at the very end if I have time. But this is not a bad cartoon, as it turns out. This is roughly what we see when we turn Alma's eye onto some of these disks. But I don't want to talk about the structure, however interesting these are. I want to talk about the chemistry of these disks. And then I have to go to an even, let's say, coarser cartoon of what's going on, because chemistry adds so much complexity in itself. So this is a cross-section what we think of how we think about these protoplanetary disks from a disk chemistry point of view. And first of all, I want to draw your attention to what's going on here. These disks are not static objects. There are lots of dynamical processes going on that moves material around, both on large scales and small scales. Now, when I told you that this happens, I'm going to ask you to forget about it for roughly the next 40 minutes and instead focus on the much more smoother, static-looking right part of the disk. Not because this isn't important. It's actually really important. But we have to start somewhere, and we're starting by looking at processes where we think this is not that important for the chemical structure. So if you turn your eyes to the right-hand side of the disk, what's really depicted there, the main thing you see is that these disks are characterized by thermal gradients, both in the radial direction and in the disk height direction. So in the radial direction, I think it's easy to, very intuitive. The further away you go from the star, the cooler it gets. The reason you have also vertical gradient is that exterior to few AU, the thermal profile of these disks are mainly set by radiation from the star. And this radiation intercepts the disk surface when you have a flare disk, and therefore you have a hotter surface and a cooler midplane. Because you have this thermal gradient, you will have phase changes of volatile material as you go further and further away from the star. In particular, you go from having major volatiles such as water going from being mainly vapor to being mainly condensed out onto grains. And this mid-plane location where this happened, we call a snowline, which we think are very important. The other things that are important is that you have a lot of energy input going into these disks. You have basically thermal radiation, you have UV, you have X-rays. This means that you have energy to break chemical bonds and therefore form new molecules. And when I go into the second half of my talk, I will be going back to that chemistry. But for now, I just want to focus on this condensation process and what that does to planet formation. One thing that we think it does to planet formation, at least that it did in the solar system, is that it changes the mode of planet formation. It changes what kind of planet you form. If we look at our own solar system, there's a clear difference between the inner 4 rocky planets and what happens exterior to the asteroid belt, that is Jupiter. It is so the orthodoxy of the field, though whether we have proven this beyond all doubt, I'm not entirely certain of, that the water, did you have a question or no, sorry? That if we looked back to the early to the young solar nebula, so before any planets had formed, that we had this transition for water between water being in a vapor phase and water being frozen out, that it happened on the scales of a few AU, maybe 4 AU. And therefore that we had grains that are mainly silicates, maybe some carbon in the inner 4 AU or so. And if we go beyond that water snowline, you have grains that are covered with water ice. As grains clump together in the first step of towards planet formation, you then get rocky planetesimals in the inner solar system and icy planetesimal in the outer solar system. And eventually, we think that that difference between the rocky and icy planetesimals lead to rocky planets versus gas and ice giants. Now, there are several different reasons why you might expect that kind of change in planet formation happening around the snowline. I mean, the simplest one is that you just add a lot of mass into the solids, which gives you a bit of a head start to form those first pebbles. Icy grains are definitely stickier than rocky grains. So you would expect that process of coagulating to forming larger and larger bodies would be more efficient when you're exterior to the snowline. We think that if two boulders that are icy collide, you have a lower probability of breaking it apart compared to if they are rocks. You have just different material properties. And there are also different kind of interactions between dynamics and condensation that can happen around a snowline that can lead to very rapid buildup of material, so right at the snowline. So I think it's not a bad idea that this where the snowline happened, that it really did. Let's say that it's not a coincidence that where we think the snowline was and where we had this change in plant formation. We think there's really some underlying physics that led to that outcome. Now, water is certainly a very important volatile when we look in general in interstellar environments, but it is not the only one. So these are all spectra that are taken in the infrared toward young stars, and what we're seeing is so if you only had some sort of diffuse non-chemical medium between us, just some fine dust grains between us and those stars, you would see a smooth distribution here, something resembling a black body. But what we do see is we have these very broad features superimposed on the radiation that's coming from the protostar. And we can identify those different features with different molecules in the ice frozen out onto grains between us and the protostar. And water is very prominent. I mean, water is a very abundant volatile. But we also see a bunch of other molecules, and including CO and CO2 being the second most abundant ones. And when we look towards large samples of solar-type protostars, we can start putting together some sort of sketch of what the typical volatile abundance is during the early phases of star formation. So if water is so the bars here, the blue bars, show the medium composition that we have during solar-type star formation. And then these sort of arrow bars show the range between the first and the third quartile. So the first thing to note is that water is, in most cases, the most abundant ice that we have during star formation. But CO and CO2 are common as well, at sort of 20 to 30% level typically, but up towards being similar to water in the most extreme cases. And these are going to be the three most important for now, and we'll come back to these minor constituents, methanol, ammonia, and methane, in a little bit.
So these are the results of fitting models to the spectra that you just showed for a large.
Exactly. And this actually question gives me a chance to bring up how you do that, because the reason we can identify what these molecules are is because we have laboratory experiments doing the spectroscopy of analogs to these interstellar ices. But and what these laboratory experiments also give you is a band strength. And when we identify things correctly and then apply this band strength, we can calculate the column density of these different molecules in the line of sight. And from there, we can derive something like this.
You get these lines where water is in the form of ice.
Sorry?
If you have ice, would you see the water line?
Yeah, so these are. Sorry, so I'm not sure I understand the question.
Ice versus liquid water.
Yeah, so these. So this is actually a subtle question in some sense. So what we see here is all what's in the ice. If it was in the gas, we would see actually a range of much more narrow features, which would be the row vibrational transitions of the molecule. Since it's in the solid, we don't have rotations, so we only get these sort of broad vibrational features. Now, this does not look like the kind of ice that like the kind of feature that you would see if you looked at water ice around, I don't know what it is in American, around in the 20s, I guess, right below like a bit below the freezing point of water. You would actually see something that looked much more structured, because the ice we're used to here is a true crystalline ice that has some very specific modes of vibration. What we're looking at here are amorphous ices. So it's actually something like a liquid, even though it's frozen. And that's why you have this unstructured, broad spectral features. So when we think about that we have more volatiles than water, what that implies is that when we look in a disk, is that we don't have just one single snowline. We have a sequence of snowlines belonging to different volatiles. Especially water, it turns out, is one of the least volatile of the volatiles. So that's pretty much going to set the boundary between having bare grains and having grains covered with ice. But as we go outward, we will get more and more different kinds of ices condensing out onto these grains, which will change the material properties of these grains, as well as leading to potential discontinuities in the column densities in these disks at each of these snow lines, and therefore potentially changing the mode of plant formation as you go outward. That is not the only effect that these sort of series of snow lines have. They will maybe even more obviously change the composition of the gas and the solids as you sort of walk out in the disk. So what this is shown here is on the x-axis is a radius in a disk model. We're looking in the mid-plane of a disk. On the y-axis is in this case the carbon over oxygen ratio. In the top here in the gas and the bottom in the solid. So if we start looking at, and these sort of sharp transitions here mark the locations in this particular disk model where water, CO2, and CO condenses out. So where we have these different snow lines. So if we start looking at what happens at the water snow line, well, you take all the water that was previously in the gas phase and you put it into grains. And as a result, your carbon to oxygen ratio in the gas will go up because you just moved a bunch of oxygen out of the gas phase. And you will end up with these grains that have mainly water on them. As you cross the CO2 and CO snow lines, you will have, analogous effects. As you cross the CO2 snow line, you will increase the carbon over oxygen ratio again because you are removing 2 oxygens for each carbon from the gas phase. And that will actually give you a carbon to oxygen ratio in the gas, which is unity, since the main carrier of carbon and oxygen is CO, is the only thing that's left in the gas phase. And you will have a change in grain composition that becomes more and more carbon rich. So if we're thinking about gas giant formation that are accreting their gaseous envelope from the gas phase, we are very interested in that you might be able to change the composition of those. And there are evidence that are exoplanets that have this weird, like weirdly high carbon to oxygen ratio, which might signify that they formed very far out in the disk, where you can get this high carbon to oxygen ratio in the gas. And we're also interested in this changing composition of the icy grains, since that will change the composition of planetesimals, such as asteroids and comets, which may at a later state be delivering the volatiles to places like Earth. So there snow lines of different kinds have potentially a large impact on the kind of planet compositions that you end up with. So we would like to know where they are at the different epochs of planet formation. This this actually turns out to be maybe a trickier problem than you would think it should be. Fundamentally, where snowlines are, where a snowline is for a particular species, depend basically on 3 things. One is the temperature profile of the disk. This is actually surprisingly difficult to measure, but we have some ideas of what they are for at least some disks that we have characterized quite well. So we're going to put that one aside. The second is the binding energy of the molecule to the grain. So the reason the water snowline is much further in is that water binds much more strongly to these grains than CO2 or CO does. And then the third thing is the dynamics of the disk. And I want to start with this question about how really sublimation and dynamics interact to tell you where these snow lines should be in a disk, assuming that we know that are two, that is the binding energy and the temperature profile of the disk in question. Sorry? So that is an excellent question. We don't think that it affects where these snow lines are here that are in the midplane. However, they may cause a second set of a second sort of outer boundary kind of snow line to happen, and I will actually come back to that. That this UV photodesorption does have an effect for the overall structure, but it doesn't. But here it's really the thermal profile that dominates. Exactly. I mean, I will come back to exactly that question. That once you get far enough out in the disk where you have this low density flared kind of disk, then photons can propagate quite far into the midplane and really affect the distribution of a molecule between the gas and the solid. But here we're still pretty far in and we're deep into the midplane. So here UV photons don't make it down here. So what's shown here, so if we just look at the black solid and dashed lines first, that is basically what was on the previous plot. So that is the carbon to oxygen ratio expected in the gas and the solids if you just had a static disk where things were not moving around. We just calculate the steady state between condensation and sublimation at each radius dependent on temperature. Then you get these black dashed and solid lines. Now, if we take into account the process of grain drift, or like pebble drift, things will start happening in this disk. So this is a very sort of simple idea that seems to be really important in disks, which is that if you have a solid body of some sort, like a planet around a star, it wants to orbit at the speed told to us by Kepler's law. This is true also for a pebble. It wants to go at that speed. However, if we're looking at the gas in these disks, and these are gas-rich disks, they feel a pressure from the gas, the more dense and warmer gas that is interior to the package of gas we're interested in. And because of that, it will be orbiting the star at a different velocity, at a slower velocity compared to a planet would. Now, a planet doesn't care if there's a bit of gas that is going slower. And tiny grains don't care because they will just get mixed up with the gas and follow in this slower velocity that the gas is moving at. But if you have a pebble on the size of a centimeter up to boulders or a meter-sized boulder, they will care. They will try to orbit at the Keplerian velocity, but they will really feel the headwind from the gas. And because of that, they will lose angular momentum and start spiraling inward. And this can be a very efficient process for centimeter to meter-sized objects. And it can be so efficient that a pebble can cross where the snow line should be by quite a bit before sublimation has caught up with this drifting, inward drifting velocity. So what's shown here, if you look at the colored lines, is just how far in this drift can happen if it's not stopped by any substructure or anything else that's going on in the disk. And this radius here is at a logarithmic scale. So if we focus in on the CO snow line up here, you can change the CO snow line location by about a factor of 2 through this process. That is like in the solar, I mean, if we think about the solar system, that's the difference between having where the ice giants and Jupiter is, right? Or ice giants and Saturn. This is a big difference when we're thinking about why a planet might have the composition that it does. If we take into account that there's also accretion going on in the disk, which is moving the gas, you get a slightly different picture, but the overall conclusion is the same, that you can move these snow lines by about a factor of 2 because of this dynamical process. The problem gets worse if we take into account the uncertainty that we have in the binding energy of different molecules. And it's not really an uncertainty in the theoretical sense, because we have laboratory experiments, so we can measure what the binding energy of these molecules are in different environments. But as you will see, it really matters exactly what environment we have, and we don't know exactly what the grain and ice environments are in these disks.
So you're talking about the binding of the molecule to the grain?
Exactly.
So that must depend on the geometry of the grain or the physical nature of the grain? Or
So it depends a little bit on the geometry of the grain, but once you have grown grains beyond sort of hundreds of angstroms level, the curvature of the grain doesn't matter that much. And once you have built up the initial layers of ice, the sort of fractality or porosity of the grain doesn't matter that much. So actually the biggest thing, as you'll see, is what that matters is what else is on the grain. And that is something that we can go into the lab and measure. And the way we can measure it using setups like this, so the main part is that there's a big vacuum chamber with the 4 Kelvin cryocooler going into the center where we build up our ice. But in cartoon form, what we can do in the lab is that we can build up with quite some precision, very thin ices of specific compositions. And with thin, I mean a few molecules thick. So we can really do the same kind of thicknesses as we have in different interstellar environments. And we can set the composition at sort of molecular layer scale. So we can really simulate the kind of compositions that you have in these grains, especially in this case, whether you have water and in what form water is, and how that affects the other molecules that are condensed out onto these grains. And then we can inject energy into the system, the same kind of sources of energy that we have in space, which means thermal energy, electrons, UV, X-rays. And in this case, we're just going to look at what that does to the sublimation or desorption of the molecules. I'll come back to the chemistry later. And we're even going to make it even simpler and only think about the thermal desorption, because that's how we measure these binding energies. So the kind of experiments that we do then is that we take one of these thin ices, we heat it up with a linear ramp, and then we measure the sublimation rate as a function of time and temperature, which have just this very simple linear relationship. And by modeling those curves, we can determine what the binding energy was that for that particular ice. So as shown here are 3 of those desorption curves for CO and N2, 2 of the most abundant volatiles during plant formation. And what they look like when we have a pure ice, when we have a compact water ice, and we have a porous water ice. And the main thing to take away is that, again, you can change the binding energy by about a factor of 2, which means you change the sublimation energy or sublimation temperature by about a factor of 2, which means that you change the snowline location by, as it turns out, potentially a pretty large number. Yeah, sorry. So this is when you have water. First of all, just having water ice. So looking at comparing this curve and this curve. Suddenly what matters is not how much CO binds to other CO molecules, but the binding energy. And this is really a bond. I mean, it's not the chemical bond, it's a physical bond between CO and water molecules become what matters rather than the bond between CO and CO. And the CO binds much more strongly to water molecules than it does to other CO molecules. So that explains the difference between these curves and what's going up here. The reason you have a little extra peak here in front, that's just the CO that we're binding to other CO molecules that comes up first. Now the difference between this curve here and this curve here is that I changed the structure of the water ice. So here we made the water ice as compact as possible, which means that each CO molecule can only interact simultaneously with a few other water molecules. Here we made it as porous as possible, which means that now a lot of the CO molecules sort of sit in a little water cage and have many different interactions, pairwise interactions with water molecules at the same time. And that increases the effective binding energy. Does that answer? So please repeat the question. I will try to answer that one.
Well, this is an exponential process, so why isn't this
Okay, sorry, that I can also answer. So what happens, absolutely, is an exponential increase as you go up here. Here you run out of material. So that was like a much simpler thing to answer. And the reason, I should say, the reason that you don't have, so here you have a pretty sharp drop off when we have in the pure ice case. The reason you have this smooth drop off here is that here you have a distribution of binding sites. So really what you would fit are a bunch of curves with a sharp drop off here. So if we're thinking about this in a protoplanetary disk context, if we're dominated by CO freezing out onto water grains, we would expect the CO snowline to be further inward. If CO is mainly binding to other CO molecules, then we should have it further outward. And if we combine this drift process and the range of potential binding energies into one model, we get the two figures shown here. So this is similar to what I showed you before, again, focusing on the CO snowline, how we just, assuming that we have pure CO ice, and we take into account that we have this uncertainty that we don't know how much the grains are drifting, we get this sort of factor of 2 difference in the possible CO snowline. If we now redo the same exercise, but assume we have the porous water ice, we also get about a factor of 2 difference for this porous water ice model, but now the innermost possible CO snowline has moved in to 9 AU, while in our most somehow pessimistic drift and composition scenario, it was at 65. So based on these sort of, I mean, these are still more or less toy models, but based on these considerations, we have a huge distribution in potential snowline locations for each of these volatiles. And that means, of course, that you need measurements. Actually measuring where the snowlines are in real disks that we think we understand. This turned out to be a bit trickier than we had first imagined. But I think the most straightforward way you would want to go about doing this is just observing gas phase CO in one of these protoplanetary disks and check where the CO gas disappears. Spatially resolved, exactly. So basically just image the CO gas and seeing where the CO gas goes away. This turned out to be trickier than we had imagined because we hadn't thought about how important it is that you have not just this radial temperature gradient, but also the vertical one. Which means that even beyond the CO snowline, you will have a lot of CO in the gas phase in the upper layers of the disk. And that is something that is very easy to get tricked by, as we discovered. And trying to model or sort of extract the CO snowline out of these images, which often have a very subtle difference in the CO emission happening around the snowline, is very difficult. Because there are other things than CO freeze out that can cause a small decrease in CO column density. For example, that you have an overall decrease in the gas column density because you have no independent tracer of the gas. So instead, what we came up with as an alternative way of determining where the CO snowline is this chemical scheme shown here, which is one of the simplest and most straightforward astrochemistry slides I think you will ever see. So enjoy the simplicity. There will be more complex things to come. Sorry? There are electrons, and I'm going to actually explain where they come in this scheme and in general. So normally we have this balance between CO freeze out and CO in the gas. Now when CO is in the gas, it will readily react with H3+, which is probably the most abundant ion that we have in these disks. It's just molecular H2 with a proton attached to it, to form HCO+. To go from HCO+ to CO, you would have a reaction with recombination with an electron. So that's where that comes in. N2 is probably the most abundant nitrogen-containing molecule, and it has an analogous reaction. So in the N2 will react with H3 plus to form N2H plus, and it will also has a recombination reaction to form N2. But in addition to that, N2H plus, if it meets the CO molecule, you will transfer that proton to the CO molecule to form HCO plus. This is the reason you have that is analogous to, I think, what's a more familiar concept, which is that atoms and molecules have different electron affinities dependent on their polarity and charge distribution and the like. And just as you can have different electron affinities, you can have different proton affinities. And CO has a much higher proton affinity than N2. N2 has a higher one than H2, which is why this reaction happened. So because of that, as long as you have CO in the gas phase, you will never form large abundances of N2H plus because it will lose its proton pretty quickly to CO. When CO freezes out, the only destruction mechanism of N2H plus that remains is this recombination with an electron, and that is much, much slower because these disks are not that ionized. And that leads to an expectation, which is that if you look interior to the CO snowline, we should not see any N2H plus there. If we look exterior, we should see it in this mid-plane region where CO is frozen out. And in an image, that should show up basically as a donut where the inner rim traces where the CO starts freezing out. And when we turned Alma towards one of our disks, TW Hydra, and we looked at N2H plus, we see exactly this kind of donut shape that we expected, which gave us an initial pretty good estimate of the CO snowline of around 30 AU. I think with a little bit more subtle modeling than we did in this discovery paper, we would probably push it inward by at least 5 AU or so. There were some things we did not take into account when it comes to the sharpness or non-sharpness of this inner edge of the N2H plus. But still, it works. We actually can say where the CO snowline is in a disk. No, you shouldn't, unfortunately. I know, it would have been so nice. So I think it's, and this is actually a general word of caution with these observations. So these are all taken with an interferometer, which means that the data you get is not an image like this. It's flux and phase as a function of telescope or dish pairs. And then you do an inversion, basically a Fourier transform, to get the image. And then you try to take into account for the fact that you didn't have a perfect coverage of baselines to clean up the image and make it more looking what the real emission distribution should look like. But part of this cleaning process, and it's really called clean, is to try to is basically putting in point sources of emission when you're reconstructing your image. And this intrinsically lead to a clumpy looking image if you have low signal to noise. So you can't really apply the normal sort of 3 sigma criterion looking at the RMS here and here to say what's real. You have to actually model the original phase and flux distribution that comes. And when we do that, this is consistent with just a smooth ring. So max entropy reconstruction. Sorry?
So maximum entropy normal would not show any structure.
That would be my expectation.
You said that you could not look at CO directly because you were confused because of the layering. But why doesn't this also, the fact that there is CO in there, why doesn't it affect these?
It doesn't affect it because this shows us as the negative of the CO gas image. So here, if we go back to this image here, so we don't expect to see any N2H plus here, which is good interior. It's also not going to show up here in the atmosphere, but we don't really care about not seeing N2H plus in the atmosphere because what we're interested in is what's going on in the midplane. And there we will see N2H plus wherever CO is frozen out.
No other likely
there is some subtlety to. So if this is far more ionized than we think it is, you would definitely increase your NTH plus destruction. But I would say that observations in theory would suggest there's maybe less ionized than we thought it was, at least when we get down into these midplane regions. There is, however, something that I wasn't going to talk about, but there is, I guess, a subtlety that is worthy of reflection, which is that having CO freezing out is not the only way to remove CO in these disks. And that is probably the biggest source of uncertainty, is that we might lose CO chemically before we lose it physically because of this condensation process. And that might trick us into thinking that we're seeing the CO snowline when we're really seeing the CO sort of chemical destruction line. So there's definitely some subtleties that goes into understanding the chemistry in more detail than I have shown you here. So the figure I showed you before, that was from 2013. We have one more disk since then. And I think there's nothing worse than having a two object sample, because there's no way they're going to be the same. And that was definitely true for these. So TW Hydra, another figure here, and then another disk HD16326 to your right. We find that the condensation temperature of CO in these two disks is about 10 Kelvin different, which is about 30% different, or 50%, depending on which one you use as your reference. This might be due either because we have different dynamics in the disk, or because we have different kind of grains in the disks. These are two very different objects. One is an A star, one is more of a solar type star. But with only two objects and several different potential causes, we of course can't tell why we have this difference. So the temperature estimates are coming from, so we measure the radius of the snowline, right? And then these disks have been, their temperature radial and vertical temperature distribution have been modeled using a combination of the spectral energy distribution and the continuum data from places like Alma that gives you what the dust emission looks like. And there are uncertainties in there. But it seems we basically use the same kind of technique for both these disks. So even if the absolute values, there are some uncertainties, I think it's clear that there is a difference in where CO is freezing out in these two disks. We have another 5 coming that have been observed by Alma. Some of them have also been reduced and sent to us. So hopefully that will give us a little bit more insight of why we have these differences in different disks, and whether it's dynamics or chemistry that is the main culprit. The uncertainties of the temperature distributions are unfortunately not possible to give you normal, I would say, sigma errors to, because the way that these were modeled was not using, say, an MCMC kind of simulation or anything like that. So I cannot give you what the uncertainties is. What I can say is that there's no model that has been attempted that could move the temperature distribution for one of the disks and not the other so much that this would cancel out. But it's two disks, and that these disks are so different that there was some bias that we don't understand that affect one disk and not the other. I cannot say for certain. And I think having a sample that's more than 2 disks is the first step towards actually understanding that, and especially having a few more in each class of objects, having a few more tutorial disks and a few more Herbig-Ae disks.
So the effects of the dynamics of the disk that you showed us before, is that taken into account here? Or do we know the dynamics of the disk?
It is not taken into account because we don't know how fast grains drift in these different disks. So that depends on the combination of the grain distribution, which we have at best qualitative constraints on.
So could the
It could.
Difference. You showed us before that it can
It
give a
could.
large difference.
It could. We just don't know if it's that or if it is the chemistry that's causing this, or even if it is some weird, unfortunate bias that we are not accounting for, because these are two different kinds of
So it's
sources.
not too surprising that it's not the same.
It is. It is not. Though I should say that our sort of theoretical musings came after we saw this, even though I presented it in the opposite order. Um, it is not too surprising, but we don't know what the source is, like which of these it is at the moment. Yeah. So the so even if you assume that you have the normal interstellar cosmic rays penetrating, first of all, making it into the disk, which there are questions about, penetrating all the way into the midplane, the kind of UV and electron field that you would generate, which is what would cause absorption, would still be very low compared to what would be needed to sort of move the snow line around. And it's simply because the density is so high, so freeze-out is very fast. So unless you have a very extreme, so not anything that you would get in any of these. So in addition to giving us the first constraint about where the sort of CO snow lines that we were looking at were, Alma observations are also providing a few surprises when it comes to snow lines. This is actually coming back to your earlier questions. And that is that we don't just have one inner snow line, but we also seem to have an outer one, which we had not expected. So what's shown here is a disk, AS209. So it's the continuum profile, and then 12CO, 13CO, and C18O. We expect the C isotopologues to have roughly the same distributions. There is some subtlety in there. But so that the difference in radial profile, we think, is mainly the cause of having different optical depths. So once you get to C18O, you're optically thin, and you're really tracing the true CO distribution. And what we see is we get this decrease in CO as we would expect due to a combination of that the overall gas profile of the disk is going down and also freeze out. But then we get this bump. And this is a really significant bump. You would need to increase your CO abundance out here, but on the order of a factor of 10 to get this bump. And what we think we are seeing is that at some point we hit a place in the disk where the dust is starting to be so attenuated that UV photons can penetrate in and start UV photodesorbing the CO off the grains and getting the CO molecules back into the gas phase. Sorry?
If you look at the left-hand image, it's not totally axis symmetric. Aren't you just seeing them, or what's the scale of
So this again goes back to interferometry. When we model the visibilities, it is actually consistent with something that's axisymmetric. Even though I know it looks very clumpy, and that's the low signal to noise issue.
When I look at the scale is at 1 arcsecond radius.
Yeah.
So at the 1 arcsecond radius in the image on the left, you have those two bumps on the two sides. Is that must be causing that bump, or not?
I'm not sure I understand the question.
The bump is at 1 arcsecond, if I understand, and it reflects the image on the left at 1 arcsecond. You see the two bumps on the sides.
So it's when we average over this part here is where you get the bump here.
That's what it's coming.
Yeah, exactly. And what we think, what this coincides with this bump is actually when we are changing the grain surface distribution in the very top panels. We have lost a lot of the grain emission by that time, and it's in this sort of flattened part of the radial grain distribution. And that coincidence, we think, is no coincidence, but rather that we're now in the outer part of the disk where most of the solids have drifted inward already because it's dynamical processes. We have very little grains left to absorb incoming UV light. which allows you to both heat up the outer disk, this is something Ilse Cleves have worked on, and also UV photons to penetrate in and release the CO. And we actually see it even more clearly in a different disk using, again, a chemical trick. This time so this is using DCO+, so it's a more indirect method, but it gives you a prettier picture, so I thought I'd show it. So this shows the ion DCO+, which forms from gas phase CO and this ion H2D+. And H2D+ will increase in abundance as you go to lower and lower temperatures. And so you have sort of double effect once you get out here in the outer disk, that you're releasing CO because of this UV photon absorption, but you're also increasing the amount of H2D+ because you are in a colder part of the disk. And because of that, you get this really magnificent second ring in the disk. So it's really just tracing where C is coming off the grain, but it's sort of emphasizing it because you also get more H2D+ at lower temperatures. That there are two rings. So it's yeah, so an inner ring and an outer ring. It's deuterium. So it's a so it is really as you go to lower temperatures, it gets easier and easier to transfer to you basically push it in this direction. And this is just a cartoon on what we think is going on. So as you are in the outer disk, things can penetrate, CO gets off the grain, and because it's low temperature, you get this extra H2D+, which gives you the excess DCO+. So you can do it with 1 of 4, which is what IM loop this particular disk is sitting in. And this is a recent paper by Ilse Cleves that shows that. So you don't need any crazy field, mainly because in this case you're so far out in the disk, so you are really in a very attenuated part of the disk.
You're no longer in a star forming a core by itself.
Exactly. These are all disks that are fairly mature in some sense. IM loop has a little bit of cloud material, but it's very tenuous. And AS209 is also free of cloud material. So these are already at the million or older disks that are free of their natal cloud, more or less. Otherwise, yeah, you'll probably not be able to do it. So because there has been a lot of questions, I am going to take the second part, select parts of this second part. So if you want to know about any of the slides I'm skipping over, you can just ask me afterward. Because I want to spend now a few minutes only talking about the likelihood of exoplanets that are in the so-called habitable zone, that they are chemically habitable. And I'm actually not going to talk about water at all. There's an excellent paper by, again, Ilse Cleves that shows that water is probably quite readily inherited from the birth cloud into the disks. And we know that when you are in the birth cloud, you have tons of water. So we expect that actually most planets form in disks that are rich in water, and that is not a problem. Instead, I want to talk about the availability of small organics for these planets. And when we try to compare, what level of organics is needed, in some sense the only thing we can compare with is the solar system, where we know we had enough of the right kind of organics around to have the origins of life. And we can't compare with planets, because on planets things have changed, compositions have changed. But we can compare with comets that should preserve pretty much what the original protoplanetary disks looked like when planets like Earth assembled. So this shows what a typical comet looks like chemically, where the area of the molecules scaled to its abundance. So water is very important. You have lots of C and CO2. But then on the few percent level, you have all of these small organics, things like methanol, methane, ammonia, methyl cyanide. And we think that that is what we want to try to compare with when we're looking towards outer systems. And I'm going to skip over this. And go here, which is to say that just as we know that water is very common in the early stages of star formation in these star-forming clouds, we also know, both based on theory and on observations, that different organic molecules are common at these early stages. We think from laboratory studies, we know how they form. If you have your initial ice, I said there was ammonia, in addition to water, CO2 and CO, you had methanol, ammonia, and methane. In that initial ice, with just a little bit of UV present, you can break apart a fraction of that ice into radicals, and those radicals can recombine as you get into the warmer parts of a protostar or protostellar envelope to form larger molecules. And these molecules, when they get very close to the protostar, they sublimate into the gas phase. And we can test these theories by observing what's going on here in protostars. So of course, what we're really interested in is whether they survive incorporation into the disk. And when we do observe these complex organic molecules, and we compare the ratio to the methanol that's observed in the same sources, we think methanol is one of the most important starting material. Well, the good news is we generally do see them. It seems like in general we do convert some of this initial methanol ice into more complex species during star formation. There are two questions, though, that this raises. One is that what's shown here is a different kind of abundances that we see. In this case, it's rather small, but still the biggest that had been observed sample of solar-type protostars. We see about a 2 order of magnitude spread in this chemical richness, let's call it, of the source. And we don't know whether that's intrinsic or an evolutionary state thing. And the second thing is that we don't know whether this chemistry survives formation of the disk. And which, yeah, I guess is shown here. So we know that when we're up here, we have this rich chemistry. But for planets, we need to know whether we still have it when we are in the planet-forming stage. And the most popular way to estimate whether something formed cold, so in the birth cloud, survived incorporation into the disk or into a planet, is by looking at the isotopic signature in that molecule. So this shows a plot of 50N over 40N compared to deuterium and hydrogen in different molecules in different solar system objects. The main thing is that the comets, which are supposed to be this pristine material, has both high 50N and high deuterium abundances. Earth, Moon, and chondrites are something in the middle, and then we have gas giants, which pretty much indiscriminately just took any kind of material in the solar nebula, have the lowest. And the general idea, which I sort of introduced before, is that as you go to lower temperatures, you put more and more deuterium into this ion H2D+, and once it's there, that deuterium can be transferred to a bunch of different molecules, including hydrogen cyanide to become DCN, DCO plus instead of HDO plus, and so on, and HDO instead of water. So the key step is really that you need to form this ion, and this happens at low temperatures. So the idea is, in general, if we can see what this isotopic composition in our solar system and in disks compared to with the earliest stages of star formation, we should be able to tell how much of the initial material that survived. And the other option would be that the chemistry is pretty much reset in the disk, and that becomes much trickier to figure out how much of these initial organics that survived. So with Alma, we can observe what these patterns in deuterium enrichment and patterns in nitrogen enrichment look like. And what's shown here, and I'm going to draw your attention to a very specific part of it shortly, is just images of DCO plus and HCO plus, and DCN and HCN in 6 different disks. So each column is a disk, each row is a different molecule. And I'm going to focus in on DCN down here, since that is something that's frequently measured also in the solar system and also in the earlier stages of star formation. And really the only thing I want you to see here is that the distribution of DCN, which should trace this efficiency of this deuteration process, looks very different in different disks. You have everything from very compact kind of distributions to something that looks very diffuse. What this is already suggesting is that this is not a pure inheritance kind of scenario, because the temperature profiles of these different disks, at least these first four, is not that different. So if you just inherited and then this DCN to HN ratio was set by some sort of sublimation condensation efficiency, you would expect to see something rather similar between these different disks. We do not. We see different patterns. And this suggests that you really have a very active organic chemistry in the disk, resetting what was originally resetting rather than just relying on what was originally delivered to the disk. This is confirmed when we look at these disks in more details. Don't really want to spend time on it. You can ask about it later. Basically, there's definitely an active organic chemistry going on in these disks. You do not just have what you started with. And instead, I want to go to what I think is the most important, which is that luckily Alma is giving us a direct eye onto the organic chemistry of these disks. It is allowing us to directly go in and measure what the organic compositions are at these stages of plant formation, sort of allowing us to bypass all of these different caveats about that when we look at the earlier and previously much more accessible stages of star formation, that organic chemistry might not survive. We don't know if we're tracing different stages, we're seeing sort of evolutionary sequence. And instead, we can just turn the telescope onto these protoplanetary disks and look at organic chemistry directly. And what we see, and this shows the first result, looking at a family of cyanides, which it turns out are very important for the currently most popular origins of life scenario on Earth, is that, well, first of all, we detect this family of cyanides. And if we look at their relative abundances and compare it with comets, where we see the same kind of molecules, it looks very similar. It really looks like the composition within the uncertainties, the composition of this disk and the comet-forming region of this disk looks identical to what comets look like in our solar system. Now, this is one disk, and we also have very few comet measurements, as it turns out, of these slightly larger molecules. So I wouldn't go out and say that all disks are going to have the same kind of organic chemistry as we had in the young solar nebula. But it would be very strange if the first disk where we managed to detect these organic molecules happened to be rare in its composition, right? So we're following up with another 5 or 6 to start with to see whether this holds. But it does seem like we are not that unique when it comes to the chemistry, which is good news when we're thinking about the possibility of origins of life elsewhere. So with that, I would just like to summarize that when we're thinking about plant formation, where it's the efficiency, the bulk composition, or the access to water or other molecules we think are important for origins of life, that's in some fundamental way that is all set by the chemistry that goes on in the protoplanetary disks. Snowlines are really important part of this, both for setting the physics of plant formation and for determining what kind of chemistry you can end up with on the nascent planets. And the good news is that Alma is really allowing us to measure where these snowlines are. We have CO, we will try for some of the others in future cycles. And it's also allowing us to directly see what the organic chemistry looks like in these disks. But I want to end with that even Alma can only give us an instantaneous look at these disks. It can't tell us what happened before or what's going to happen in the future. And even with Alma, there's going to be the majority of the chemistry will be hidden to us. And the only way that we can get a holistic view of the chemistry in these disks is really by combining these Alma observations with theory and with especially laboratory experiments. And with that, I want to thank you for your attention.